Hi everyone. In this lesson, you will learn how a program can efficiently handle request messages. This concept will be illustrated through an example of interaction between two programs. Let's say you have a cool application with its own unique features, right? Now you want to update it a bit by uploading a new version to the blockchain. But here's the catch. As soon as you do that, the app's address on the blockchain will change. And you don't want to confuse your users by making them deal with a different address every time, do you? That's where the Proxy program comes in. It acts as an intermediary. Users send their messages to Proxy, which then passes them on to an updated version of dApp. And when the dApp responds, Proxy passes those responses back to the users. So, every time you update a dApp, all you have to do is update its address in the Proxy program. Easy and simple, right? Alright, first things first, let's set up the directories we'll be working with, including the one for our Proxy program. So now we're going to dive into the code. Open up the main file, cargo toml. This is where we list all the dependencies we'll need. We want to connect to the GSTD library. And while we're at it, let's connect the IO directory. But wait, that's not all. We have to take care of the build dependencies section as well. This is where we plug in the gear wasm builder, and yes, you guessed it, the IO directory again. Gotta keep things running smoothly, right? Let's not forget about the IO directory. It is there for a reason. It also has its own role to play. When we install dependencies in IO, it's not just about the GSTD library. We also have to add gmeta. It is the one that describes the metadata. Make sure everything is properly labeled and organized. Let's get into the intricacies of setting up the IO directory. We get right to the point. We specify that we are building a program without using STD. As for connecting libraries, let's lay the groundwork first. We'll leave the library slots empty for now. Don't worry, we'll fill them in as we write. Now let's move on to creating the proxy metadata structure. This is where we'll start to describe the essence of our program. We'll define the fields we need, keeping it simple for now. We are mainly interested in the init and handle fields. We will specify them when we realize what data we need. Now let's focus on the actions our program will perform. How about we start with a friendly hello? Maybe we'll add a how are you query. And let's spice things up with a third action that's a little more complex to keep the answers interesting. Now let's move on to the traits. We need to plug in some traits for encoding and decoding. These are tools that will help us communicate effectively so that our data speaks the same language across platforms. Actions are great, but let's not forget about events. These are the responses our program will send out. Now let's fill in the handle field for our metadata. When our program gets an action, it knows what to do, right? That's where the handle field comes into play. Actions go in, events go out. It's all about keeping things organized. At this point, our metadata is pretty well organized. We've figured out the handle field, which is a big piece of the puzzle. As for the init field, well, we'll deal with that when the time comes. To get our program successfully compiled, we need to take care of the build file. Here's how our build file should shape up. It needs to accept our metadata and then call the appropriate function to generate the file with all the metadata data. Let's dive into the basic logic of our proxy program. As always, we'll start by connecting the libraries we'll need. And as before, we'll populate them as we progress through the coding process. Now let's parse the next line of code, which defines our static variable session. And the type option tells us that it can either be empty or contain an object of type session. Since we are talking about session, let's create a structure for it. It will have two fields. One to store the address of the target program, and the second is a tuple containing the identifiers of the message sent to the target program and the user who initiated this action. Now let's move on to the init function. It is very important. It is marked as external and has the no mangle attribute, which means that it will be called when our application starts. Inside this function, we load and decode the address of the target program with message load function. This kind of lays the groundwork for our program to work. Now that we have the address of the target program at initialization, we can populate the init field in our metadata. This kind of connects the dots between our code and our metadata, making sure everything is in sync. Last but not least, we create a session object and put it in our session static variable. This part gets a bit tricky because we are modifying a static variable inside a function, so we have to use the unsafe keyword. But if the decoding is successful, we create a new session object with the received target program ID and null values for the message and user IDs. Now that we have laid the groundwork, it's time to add the necessary elements to make our program work. This means that we need to import libraries and modules that will work with our proxy program. Now let's look at the handle function, which is a key element of our program's logic. Like init, it uses the no_mangle attribute, indicating its importance for handling actions in our application. Within this function, the action sent by the user takes center stage. We load and decode it using the message load function. If all goes well, we create a variable of type action containing the received action. Next, we access the session variable using the unsafe keyword. If the session is not initialized yet, we generate a panic using expect function to report the error. It's like an alarm when something is wrong. Now we are ready to send a message with the received action to the target program using the message send function. We pass the target program ID and the action with a null value. If the send operation goes smoothly, we store the message ID and user ID in the variable inside the session object. This is like a record of who sent the message and when for future reference. Finally, to tie everything together, we send a reply message after the event has been successfully sent using the message reply function. This ensures seamless communication between our program, the target program, and the user. It is the backbone of our application, providing interaction with the target program and feedback to the user. With the handle function, our application is able to handle actions seamlessly, ensuring smooth operation and user satisfaction. All right, let's shift our focus to the second program, the target program. First things first, we need to set up the groundwork by filling in the cargo.toml file and creating the build.rs file. These are crucial for the successful compilation of our program. And just like before, we need to import the necessary libraries and define our actions and events. The target program must be aware of them to encode and decode them properly. It's like speaking the same language to ensure smooth communication between programs. Now let's dive into the handle function of the target program. Here, we're dealing with the actions sent by the user. We load and decode them using message load, and if all goes well, we create an action variable of type action containing the received action. But here's where it gets interesting. We use the match construct to handle the different possible actions. After handling all the actions, it's essential to provide a response back to the user to keep the interaction flowing smoothly. We achieve this by utilizing the message reply function, which acts as our messenger, delivering the generated event as a reply. This function allows us to send the event back to the user who initiated the action, completing the loop of communication. Of particular interest is the action make random number branch. Here, we generate a random number within a given range. It's like rolling the dice to add an element of randomness to our program. To generate pseudo-random numbers, we use the static variable seed. First, we store the current value of seed in a local variable called seed. Using the unsafe keyword, since we're dealing with a static variable, that can only be modified inside an unsafe block. Then, we increment the value of seed to ensure a different sequence of random numbers in subsequent calls. After that, we generate a random number based on the input data, limiting it to a given range. With all the necessary imports in place and any corrections made, we're finally ready to kick off the compilation process for our program. This is the moment of truth, where we'll see if all our hard work and meticulous attention to detail have paid off. All right, let's dive into writing the handle reply function, which is crucial for processing response messages in our program. First things first, we need to retrieve the identifier of the message we're replying to using message reply to function. If, for some reason, we can't fetch this message identifier, it's a red flag, and we generate a panic to alert us of the issue. Next, we access the session variable using the unsafe keyword and get modifiable reference to the session object. If the session hasn't been initialized yet, we also generate a panic to handle this exceptional case. We retrieve the message ID and user ID from the session object and check if the retrieved message ID matches the message ID of the message we're expecting a response to. If they match, we load the response message using message load, convert it to the event type, and send it back to the user using message send function. In essence, this function ensures that response messages are processed and sent back to the user, completing the loop of communication initiated by their actions. And now, it's time to put our function to the test. Let's ensure everything's working as expected by running our program. All right, let's gear up and write some tests to ensure our program behaves as expected. We'll start by setting up the testing environment in our cargo.toml file, plugging in the necessary dependencies, the gtest library, the IO directory, and our target program. Now, let's create a folder for our tests along with a test file. Organization is key when it comes to testing. With our environment set up, it's time to dive into writing the actual tests. We'll begin by creating a testing environment using system new. This sets the stage for our tests to run smoothly. Next, we'll grab the root crate program using the provided system, specifying program current. Then, we'll initialize the target program by loading it from a file. This ensures that our tests interact with the actual target program, mimicking real-world scenarios. Absolutely. Before we jump into testing the functionality, it's crucial to properly initialize both programs. Let's start by initializing the target program. We'll do this by sending it an empty message. This kickstarts the target program and ensures it's ready to receive and handle messages. Once the target program is up and running, we'll proceed to initialize the proxy program. To do this, we need to send the address of the target program to the proxy program. This establishes the connection between the two programs, allowing the proxy to act as an intermediary for messages sent to the target program. After initializing both programs, it's time to send a message to the main program's handle function and check if the target program responds appropriately. We'll send a message requesting a random number and verify that the response contains the expected information. To do this, let's use the log builder function, which helps us to specify the variables we need to know that we got the right answer. Let's check that the test is working correctly at this stage. If everything checks out, we'll finalize our test by retrieving the reply message from the mailbox using system get mailbox. We'll verify that the response contains the expected message number and write a final assert to confirm the success of our test. With our tests in place, we can run them to validate the functionality of our program, ensuring it behaves as intended. Congratulations, we have finished writing the test. Let's try to run it. Great, the test was a success. That concludes this lesson, and next lesson we will go into more detail about program interaction. See you soon.